Okay, so the topic I'm going to talk about today, not in my original line of research slash, actually even not close to my original stuff I trained in, but it was a topic that I got interested in. Indirectly, I came across an interesting idea that I can share that's related to, well, this topic. So first of all, let me kind of say what I mean when I say trace theorems for metric spaces. So this is one of the many things that has come from, like, there's this field of analysis on metric spaces, and they have a bunch of stuff that came from them taking PDE problems and working on them, and then ripping out the PDE context and just doing the metric part that interests them. And so this is one of those things. So
Okay.
So the setup, and I'm going to draw it suggestively in line with the main example I'm going to share, is I've got a metric space X, and I'm gonna, let's just make Z is going to be the boundary of X for today, and so that it's a metric space, and this is X up here, and then Z is going to be my line across the bottom here. So X bar is union. The completion of the space is the union of X and Z. And I also so, as in the previous talk, our metric space is going to need to be equipped with a measure, and so the basic problem is I'm given a function u, that's for X star. So I'm given a function belongs to some regularity class that I've defined using mu. I'm going to be deliberately ambiguous about that for a moment. And you want to know if as a, well, you could say trace, you could say boundary values. We're going to say trace today. So something that's canonically defined based on U, and preferably it should belong to some other regularity class. And this is going to take the form of some bounded linear operator from some function space to some other function space. So to use the example that I've suggestively drawn, I will have X be, I'll write it this way, the upper half plane n plus 1 is greater than 0. And Z is going to be, I'll write Rn for it. So that's the part. And mu is going to be Lebesgue measure on X. And okay, so there's something I forgot to mention back here, but that the problem here, the kind of the difficulty of the problem here is that usually this thing here is a null set for this mu, which makes actually defining, and usually U is only defined almost everywhere, so makes the problem of having to actually define U on Z kind of rather troublesome.
But the metric is the hyperbolic metric. The metric is the hyperbolic metric.
No, so I'm using the Euclidean metric. This is all Euclidean. all. And so there's a, so in this context, there's a theorem due to Gagliardio that says that if you have a function u in the Sobolev space, so this P or Sobolev space up here, so it's a function whose P integrable and who's got a derivative that's also P integrable, then you get F in another space. This is a Bezov type space. And in fact, this is, you have, think of it, as I said, as like a bounded operator going from here to, I'm going to omit the things. And the interesting thing from the context of analysis on metric spaces for thinking about these things is that, so this Bezov space here is defined by the finiteness of some energy plus being P integrable that I'm going to write out that you've got a double integral over I actually don't know when I started.
You started eight minutes ago, actually, slightly less than 8 minutes.
Okay.
You just maybe 6 minutes.
Yeah, I was looking, I was like, wait, has it been already been that long? So you want, I'll put it in here for, there's like, you got a little LP norm in there that is just for LP stuff. But the big expression here is, so there's many different ways you can define these Bezov spaces. You can use Fourier analysis, which is really effective in Euclidean space. You can use difference quotients. You can do a lot of different things. And I'm going to choose to use this method here. So you can see I'm integrating twice, and we've got the difference between x and y. At the bottom here, with some exponent weight, got p power of my function up top. So here's where we have the p and the s come in. And the point that I want to make here is that this expression makes sense. And so this expression I just wrote here makes sense in any metric space with measure. So I don't want to say,
I'm sorry, I can't see the first symbol to the left of the double integral.
oh, that was just let me just omit that. Don't worry about it. Well, so I was putting in the LP norm just because I wanted to say that for the purpose of the norm is defined on the space. This function space here, I've got to insert. You got to insert the LP norm along with this, or else constant functions are going to have a zero norm. So this makes sense with sense. I'll write here a sense of dimension. You can generalize this. So for our sense of dimension, we're going to go with this Alfor's irregular concept where if I measure the mass of a ball, radius r, it measures something like comparable to r to the cube. So what I do, I plug q in for n, and this is now the distance. And now you have a perfectly fine definition. And so the tension here is that, well, it's really easy. As you can see, it's quite easy to extend Bezout spaces to these types of metric spaces. It's not so easy.
Space kind of uniform, this cube, as you go, but that's a local thing.
This should be uniform. Actually, I think it's fine if it's local. Or it depends. Okay, it depends on the problem. It depends on what you're doing. So you can see the ease with which we've extended this notion to a metric space with this kind of property. But if you go back to being like, okay, what do I do about subload spaces? This is suddenly a very difficult problem, and often essentially impossible depending on the type of metric space you're trying to work with. And sometimes your Bezout space is the best you've got. And so people wanted to be like, okay, if I'm only stuck with Bezout spaces or with metric spaces that are not cooperative with, this sort of Sobolev type structure, how can I understand these things? Because these things are terrible to work with in comparison to, having derivatives and things like that. So there's this group of people I started talking to that had this interesting idea, which was basically like, okay, I've got some metric space Z, and I want to understand some stuff about Bezout spaces on Bezout functions on Z because I want to use them for something else. So I'll put Z down here. So now Z is like a given metric space. And we're like, well, could we replicate this picture up here? So if this back here, Z was like Rn, and then there was Rn, the upper half plane sitting up there. And so they went ahead and took an idea. It was essentially that this idea of a hyperbolic filling where you create a hyperbolic graph from your metric space, and you kind of renormalize it according to certain function is distance. All right, that's incredibly ambitious for drawing there. So now things are like that long at that level, at this long, this next level, and there. This long at this level, and things are basically, you got some graph. It's built from structure, the data you get from Z, more precisely the various nets of points in Z at various scales. And you renormalize it so that you are essentially have a distance, or you are making things exponentially smaller as they get closer, quote unquote, closer to Z. And you create this picture where you have a metric space that has that is essentially, bulk of it here is a metric graph, and it has this starting metric space Z as its completion. Yeah, I'm still not no idea where I am on time, but I'll finish up.
Almost 15 minutes. Useful.
All right, yeah, then I'm basically done here because what do I want to say? So with arbitrary metric spaces, working on any sort of Sobolev function or whatever, defining that sort of thing might be possible. But for a graph with a metric on it, this is very possible. And so you might have some measure nu down here, and you would lift it up to a measure mu up here. That's going to be like Lebesgue measure on each edge, but with some weight. And you can define a Sobolev space that is essentially what you would think it is. You're using the integral functions against this mu with the gradient, the quote unquote derivative being, well, oftentimes these functions are, you can basically determine what's going on from the values at vertices. And so it's basically the Euclidean gradient you think of on each edge, and then you integrate all that stuff up and get some norm. And the conclusion was that you can do the same thing as what we wrote before, that you can think of these Sobolev functions on here as coming from these Sobolev functions on here. And then the trick is that you can derive a bunch of properties about these guys from the fact that actually this extension also can be thought of as extending a Sobolev function from x to x bar. And so you can use facts we have learned about how Sobolev functions behave on this sort of metric space to derive via restriction interesting facts about Z. And that's pretty much it. All I have to say for now.
Questions?
Who is BBS? Maybe I missed it.
That was the group. Oh, I never said the name. That's the group that I learned about this problem from, and they essentially did the kind of compact version of this, where Z was some compact metric space, like say the canonical example here would now be like the unit circle, and then you have the unit disk inside, and then you have your graph here, and Z is the boundary. But there were some technical issues with taking what they did and looking at bit spaces that could be unbounded. And so what I was working on was the unbounded picture, and I ended up with this kind of thing here. And this, these people are Bjorn, well, two Bjorns, and Shahu. Yeah.
I know that you have specific goals in mind. What do you know why they were developing this?
They wouldn't tell me.
I mean, so do I understand correctly? So the interesting, one very interesting part is that the map is subjective, right? So
Yeah.
so you're able to lift any map
Yeah.
to that, like in the original Gagliardo theorem. Why is it much better than doing something like naive? Like I would have naively tried first to cross with R and look at the product space Z times R.
Because
Look at the Sobolev extension over here.
this kind of doesn't fix the smoothness issue, because you've taken crappy space, like maybe it's a Cantor set or
I
something.
see, sure.
And you crossed it, yeah.
It remains crappy, but W1V got at least a little bit better than the Sobolev. Yeah, I understand. But so in this way, you got at the same time a better space, a better function space, and a better underlying domain. That's what the point is.
Yeah. And like I said, I am actually not 100% sure what the end goal but that's because they wouldn't tell me what the end goal was, because I asked and they said they couldn't tell me. So.
And what's the end goal for you?
So I was studying something completely different, working on some problems in dynamical systems relating to classifying like systems of hyperbolic type, like non-subject dwarfisms and things like that. And these terrible metric spaces I've been talking about here, these Z's are kind of all over the place when you look at those guys, because it's basically the same stuff as what you see. The relevant metric spaces that you're looking at and kind of thinking about are basically the same as what you see as, you know, the boundary of some negatively curve, like the universal cover as the negatively curve for Monty manifold. And it's like, just as kind of crappy as that from like a regularity perspective, you know, you've got a couple nice boundaries and then you've got mostly it's just kind of crap.
So when you say you want to know whether it has a trace, what sort of properties are you looking for?
This is kind of a problem dependent. Well, I mean, because it's kind of confusing to look at in isolation. I think the initial context is, you know, you have a function that solves some equation up here, and you want to know if it has an extension here that satisfies the boundary condition that you imposed for your problem. So that's back at the PDE kind of thing, but then they have kind of just started studying the problem in isolation, where then it's no longer being very particularly clear what the goal here might necessarily be, depending on the starting point. But yeah, there's enough analogies to like the Euclidean setting that you can usually get a good idea of what you're going for.
Okay, if there are no other questions, thanks.